Okay, welcome. Welcome back, or welcome for the first time. If welcome for the first time, you should actually watch video reading 301 before watching this video. If welcome back, hopefully you've watched video 301. 301 goes over the how-to on the reading section. In this video, reading 303, we're going to do some actual practice. And in this case, we have a science passage. And if you remember from video 301, the three science passages, whether they're kind of traditional sciences or psychology or some type of social science, tend to follow the same pattern. So as an active reader, we want to be aware of what the pattern of the passage is likely going to be, and we want to look for key things. So we know what the science passage is. Usually we get a little bit of background about some, and it's popular science. So they're taking a concept that most people don't study in their day-to-day life, and it's something that's happening in academia, and they're trying to communicate it to the masses, people like you and me. So what happens is they'll start off by giving us a little background. So we kind of have some context for what's being studied. Then usually an essential question will be asked, or they'll tell us that a key discovery has been made. Essentially, they'll get to the purpose or the main idea of the passage, what new information is being reported to us. Then after that, they'll explain how they got to the discovery, or they'll explain kind of the steps they took to answer the essential question. And that's usually done through a procedure and experiments and research. Then last but not least, actually not last, second to last, is we'll get the data and a bit of analysis. Again, this should look really similar to the scientific method. And then finally, after all that, I'll kind of put this up at the top. Sometimes you'll have other scientists kind of weighing on what they think, or future steps will be suggested. So that doesn't always happen, but that's always a possibility. So other experts weigh in or future steps. Or sometimes they just kind of conclude what everything means. So kind of ties into analysis, future experiments. Okay. Anyway, if you want to try this one on your own and then compare your notes to mine, this is SAT Course Test 2. And it's the last passage, questions 43 to 52. So you're more than welcome to kind of pause this video, open this up, try it on your own, come back, and then see how your experience compares to mine. But if you haven't paused it, let's just get right into it. So let's see what the background is. So we have a passage adapted from Jeffrey Giller, Long, a Mystery, How 500-meter high undersea waves form is revealed. Okay, so they pretty much tell us what they've discovered in the title. They're already telling us the discovery. We're going to figure out how these underwater waves form. Okay, some of the largest, let me make this a little bigger, easier on the eyes. Some of the largest ocean waves in the world are nearly impossible to see. Unlike other large waves, these rollers, called internal waves, that's a key term, do not ride the ocean surface. Instead, they move underwater, undetectable without the use of satellite imagery or sophisticated monitoring equipment. Despite this hidden nature, internal waves are fundamental parts of the ocean water dynamics, transferring heat to the ocean depths and bringing up cold water from below. And they can reach staggering heights, some as tall as skyscrapers. So hopefully what you've pulled from that paragraph is that internal waves are below the surface. We have sophisticated technology to measure these internal waves, and ultimately they serve an important role. Why? What do? They transfer heat from the top of the ocean depths to lower, and they bring cold water up. So they help to mix the water within the ocean. Okay. Because these waves are involved in ocean mixing, and thus the transfer of heat, understanding them is crucial to global climate modeling, says Tom Peacock, a researcher at the Massachusetts Institute of Technology. So Peacock's explaining why it's important to understand these waves, because they control global climates. Most models fail to take internal waves into account, If we want to have more and more accurate climate models, we have to be able to capture processes such as this, Peacock says. Peacock and his colleagues tried to do just that. Okay, so now we're getting into the experiment. The experiment, so we know that the key discovery is kind of a better idea of how internal waves work. And this experiment is going to probably be an experiment on modeling internal waves so that we can figure out how these waves affect the climate. Okay. So their study, published in November in Geophysical Research Letters, focused on internal waves generated in the Luzon Strait, which separates Taiwan and the Philippines. Internal waves in this region, thought to be some of the largest in the world, can reach about 500 meters high. That's the same height as the Freedom Tower that's just been built in New York, Peacock says. Although scientists knew of this phenomenon in the South China Sea and beyond, they didn't know exactly how internal waves formed. So scientists are familiar with the idea of internal waves, but they don't know how they're formed. That's kind of a mystery. To find out, Peacock and his team of researchers from MIT and the Woods Hole Oceanographic Institute worked with France's National Center for Scientific Research using a giant facility they called the Coriolis platform. Okay, so they're essentially being able to set up their own microclimate indoors to model internal waves. The rotating platform, about 15 meters in diameter, turns at variable speeds and can simulate Earth's rotation. It also has walls, which means scientists can fill it with water and create accurate large-scale simulations of various oceanographic scenarios. So we're going to create an oceanographic scenario of the South China Sea. Or not the South China Sea, I'm sorry. Of the Luzon Strait. Where did it say that? Or I guess we'll find out. We'll keep on reading. Peacock and his team built a carbon fiber resin scale model of the Luzon Strait. So there it comes. So I jumped the gun, including the islands and surrounding ocean floor topography. Then they filled the platform with water of varying salinity, so levels of salt, to replicate the different densities found at the strait, with denser, saltier water below and lighter, less briny water above. Small particles were added to the solution and illuminated with lights from below in order to track how liquid moved. Finally, they recreated tides using two large plungers to see how the internal waves themselves formed. The Luzon Strait's underwater topography, with a distinct double ridge shape, turns out to be responsible for generating the underwater waves. Okay, so they've got the answer to their question. In this case, it's the topography of kind of the ocean floor and this distinct double ridge shape within the ocean floor that's creating these underwater waves. As the tide rises and falls and water moves through the strait, colder, denser water is pushed up over the ridges into warmer, less dense layers above it. This action results in bumps of cold water trailed by warmer water that generate an internal wave. Okay, so they figured out exactly how the internal wave happens. We've got cold water being pushed up, and then after that, we have warm water kind of having a rippling effect and being pushed up as well. And that creates a wave. As these waves move toward land, they become steeper, much the same way waves at the beach become taller before they hit the shore, until they break on a continental shelf. The researchers were also able to devise a mathematical model. So not only do they have this topographical model, but they have a mathematical model that describes the movement and formation of these waves. Whereas the model is specific to this specific topography, the Luzon Strait, it can still help researchers understand how internal waves are generated in other places around the world. So by understanding more about how the Luzon Strait waves are generated, we have a better idea of how they're likely to occur in the rest of the world. Eventually, this information will be incorporated into global climate models, making them more accurate. So that's the kind of the overarching big idea is the more we understand internal waves and how they're created, the more likely we are to incorporate them into climate models and have more accurate climate models. It's very clear within the context of these global climate models that internal waves play a large role in driving ocean circulations, Peacock says. So if you think about it, the background is scientists always knew about internal waves, but they didn't know how they were formed. The key discovery is we created a model, both mathematical and topographical, that showed how they're formed in the Luzon Strait. The procedure and experiment was actually creating the model and testing it. And the data and analysis is knowing that the topography is actually kind of what creates the waves and causes cold water to rise and bump up into warm water, which creates a rippling effect. Okay, so now that we've had a good read, and again, you get about 13 minutes per passage, so the actual reading on the test should take about 6.5 minutes. So then we'll have 6.5 minutes roughly to go through the questions. And as always, as we go through these questions, we're reading the questions really carefully, and as we go through the answers, we're saying, do I know it for certain? Was it contained in the passage? Or is this putting me in a position where I have to assume something that I couldn't directly point to a line number to get? So let's see. Oh, and we also have this model here. So we'll take a brief look at it. I always encourage taking a brief look at this before going to the questions, even though this doesn't come up until the last two questions, because sometimes looking at the model helps you better understand the experiment, because the models always relate back to the passage. So changes in depths of isotherms, and an isotherm is a band of water of a constant temperature, an internal wave over a 24-hour period. And what we see being measured, and we always have to be really careful about what's actually being measured and what isn't, is our input is, or our x-axis is essentially different temperatures, and these different temperatures at different time periods. And then our output is the depth at which these temperatures occur at various times. So time kind of affects the depth. And what we see fluctuations in all bands, that these bands kind of go up and down over time, mixing ocean currents. Okay, let's go into the questions. So the first paragraph serves mainly to, so if we feel comfortable enough, we can answer it. If not, let's go back to the first paragraph and really pin down what it says. So some of the largest ocean waves in the world are nearly impossible to see. Unlike other large waves, these roller coasters called internal waves do not ride the ocean surface. Instead, they move underwater, undetectable, without the use of special equipment. Despite their hidden nature, internal waves are fundamental parts of ocean water dynamics. They transfer heat and bring up cold water, and they can reach staggering heights. So essentially, this is just background. It's just telling us what internal waves are and why they're important. Explain how a scientific device is used. It mentions specific equipment, monitoring equipment, and satellite imagery, but it doesn't actually say how it's used. And it's definitely not the main purpose of the first paragraph. So it's not really saying how a specific scientific device is used. It just mentions a couple. Note a common misconception about an event. Well, there's no misconception. There's no, hey, a lot of people think this mistakenly. Describing natural phenomenon and address it's important. Yes, it describes internal waves, and it says that they're important in mixing ocean currents. But let's just look at D. Present a recent study. Nope, no studies presented, and there's definitely no summary of findings. Okay, for 44, they want to know how the word capture is, how it's being used in context. So we kind of have our own definition of capture. You can kind of capture a fish, or you can capture an image. But let's actually see how it's being used in context here. So if we want to have more and more accurate climate models, we have to be able to capture processes such as these. So Peacock wants to be able to kind of develop a record or data on internal waves. So he doesn't want to control internal waves. He doesn't want to secure them. He doesn't want to absorb them. He wants to be able to record how they occur. Okay. According to Peacock, the ability to monitor internal waves is significant primarily because, and this 45 is linked to 46. So we'll see if we can get this down to one correct answer. But if we can't, we can use 46 to help us. So this has to be according to what Peacock thinks or said. So it's going to be a Peacock quote. And the ability to monitor internal waves is significant. Why? It will allow scientists to verify the maximum height of such waves. No, we already kind of know how high they can go. We've already met, he mentions in the first paragraph, they can be as high as the Freedom Tower. It will allow researchers to shift their focus to improving the quality of satellite images. No, we mentioned satellite images record internal waves, but we don't talk about trying to improve quality. C, the study of wave patterns will enable regions to predict and prevent coastal damage. Coastal damage isn't really mentioned. So again, as you're reading these, you're just looking for one or two words that sour the whole answer choice. Everything has to be supported by the text. It can't be something that's not mentioned or discussed. The study of such waves will inform the development of key scientific models. And that is definitely the one we want. Let's see where we can get our proof, though. 1 to 2. Probably not. Some of the largest waves in the world are nearly impossible to say. So no, that's not talking about improving scientific models. It's probably not 4 to 6 either. Instead, they move underwater, these internal waves, undetectable without the use of satellite imagery or sophisticated monitoring equipment. So again, that's not talking about improving scientific models. 17 to 19. If we want to have more and more accurate climate models, we have to be able to capture processes such as these. So it's very important to be able to record internal waves so that we can improve our climate models. So C definitely supports D, but let's quickly check 24 to 26. Internal waves in this region, thought to be some of the largest in the world, can reach, okay, so that just tells us how high the internal waves can get, but it doesn't tell us about improving scientific models. So we definitely have D and C there. Okay, 47. Is used in line 65, device most nearly means. So we know a device can be a piece of equipment, or sorry, not device, devise. So we know to devise can be to kind of come up with a plan or a scheme, but let's actually see how it's being used in context. The researchers were able to devise a mathematical model. So in this case, they're able to make or create a mathematical model that describes the movement and formation of these waves. So they're not solving a mathematical model. They're generating one that can predict outputs. They're not imagining it. They're not beginning it. They're creating it. And you can always plug in the words you choose and see if the sentence still maintains its original integrity, meaning that you're not changing what the original sentence is saying. All right, let's look at 48. Based on information in the passage, it can reasonably be inferred that all internal waves, okay, so we want to know what we can infer about all internal waves, reach approximately the same height, even though the locations and depths of continental shelves vary. Never said anything about all internal waves reaching the same height. That's kind of an absolute. To say every internal wave reaches the same height, that's very unlikely to begin with, but it definitely doesn't mention that in the passage. May be caused by similar factors, but are influenced by distinct topographies of different regions. So we'll hold off on this one for a second. We know that they created a topography of one model of one area, the Luzon Strait, and they think that it can help them understand other areas. And we know that they think internal waves are kind of influenced by kind of topographies and tides and cold water and warm water moving. So probably B, but let's keep on reading. All internal waves can be traced to inconsistencies in tidal patterns. I didn't read anything about inconsistencies in tidal patterns. I don't know if you did. Are generated by the movement of dense water over a relatively flat section of ocean floor. So it did talk about the movement of kind of dense water at the bottom, creating an internal wave. It definitely talked about that. So D is very attractive, but it never says anything specifically about the dense water having to move over a flat section of ocean floor. So again, it's not okay for just part of the answer to be right. All of it must check out. So 48 is going to be B, but let's find our support. So internal waves are caused by similar factors, but topographies can kind of change them a little bit. So 29 to 31. Although scientists knew of this phenomenon, the internal waves, in the South China Sea and beyond, they didn't know exactly how internal waves are formed. So that doesn't really compare all internal waves. So we can just get rid of that one. Right, we have to kind of compare all internal waves. 56 to 58. As the tide rises and falls and water moves through the strait, colder, dense water is pushed up over the ridges into warmer, less dense layers above. So this is explaining kind of how the waves are created in the Luzon Strait. But it doesn't mention anything about distinct topographies in different regions. Right, we have to find a quote that supports every part of our answer choice. So let's look at 61 to 64. As these waves move toward land, they become steeper, much the same way waves at the beach become taller before they hit the shore until they break on a continental shelf. So that just describes the waves becoming steeper, doesn't mention anything about topography. So hopefully D has something on topography for us, let's say. Whereas the model is specific to the Luzon Strait, the mathematical model that they created, it can still help researchers understand how internal waves are generated in other places around the world. Okay, so this is comparing all waves in different places, and it's saying, whereas this mathematical model kind of developed from the topographical model that they made, whereas that's specific to this area, essentially understanding how waves are created here can help us understand how waves are created elsewhere. So they must share a lot of the same similarities in how they're created, even though the Luzon Strait has its own specific topography. So 49 is going to be D. Okay. Let's take a look at 50. In the graph, which isotherm displays an increase? So it's telling us to look at the graph in depth below the surface during this period. So it's telling us our input is between 7:12 p.m. and 8:24 p.m. And it wants to know which isotherm increases in depth, meaning it goes down. Okay, 7:12. So at 7:12 p.m., we look at it. These are all increasing, but as they increase, it actually means their depth is decreasing. They're getting closer to the surface. Only this band is actually increasing in depth over this period. So which band is this? This is 13 degrees Celsius, the top one. Okay, two more. Which concept is supported by the passage and by the information in the graph? So these tend to be the harder ones. It's a passage and graph one. So let's take a look. Internal waves cause water of varying salinity to mix. That's kind of discussed in the passage that waters of varying salinity kind of rise and fall. I don't know if it talks about the mixing, maybe, but the graph, if we look at the graph, it doesn't show necessarily any mixing there. So I'm hesitant on that one. I don't want to get rid of it quite yet, but let's look. Internal waves push denser water above layers of less dense water. So that's unlikely. And if we look at the graph kind of doesn't measure water density. So we just don't know. Because it's not measured in the graph, we can't pick it. Internal waves push bands of cold water above bands of warmer water. So if we look at the graph, the cold water never actually leapfrogs above the warmer water. They kind of go up and down together, but the warmer water always stays above. Internal waves do not rise to break the ocean's surface. So it's probably going to be D. Let's double check though. So if we look at the graph, sure enough, internal waves are never breaking the ocean surface, right? The surface is right here, this yellow line. And these isotherms, which are bands of internal waves, never rise above it. And the first paragraph, because we need support from the passage, says, unlike other large waves, these rollers called internal waves do not ride the ocean surface. So we can feel pretty safe in choosing D there. And the more and more I think about A, the graph doesn't measure the amount of salinity in the water. And because it's not measured in the graph, we can't pick it. If it's just not something that's displayed in the graph, then we're making an assumption beyond the graph, and we really have to be careful about not making assumptions. Only what's measured directly in the graph. Okay, 52. How does the graph support the author's point that internal waves affect ocean water dynamics? Okay, so we want to know the author's point. So this is both passage and graph. And what point does the author make about internal waves affecting ocean water dynamics? It demonstrates that wave movement forces warmer water down to depths that typically are colder. Demonstrates that wave movement forces warmer water down to depths that are typically colder. Yeah, I guess we did see warmer water being pushed down in the graph. Let's just read the other ones. It reveals the degree to which an internal wave affects the density of deep layers of cold water. Again, density is just not measured in the graph. It illustrates the change in surface temperature that takes place during an isolated series of deep waves. I wouldn't say it measures an isolated series of waves. It measures waves over the course of 24 hours. And then also, the surface temperature is never actually measured. It's just not measured in the graph. If we go up, no measurement of surface temperature, right? Here's 0 meters below the surface, and 0 meters below the surface, no measurement of temperature. It shows the multiple waves rising near the surface of the ocean disrupt the flow of normal tides. So again, the graph doesn't measure the disruption of tides. So we can feel pretty safe choosing A. And if we want support from the passage real quick, and again, we probably don't have to use time to go back to the passage on this one, but the first two paragraphs talk about cold water being brought up and warm water being pushed down. Where do we see that? We see internal waves are fundamental parts of ocean water dynamics, transferring heat to ocean depths and bringing up cold water from below. And then we kind of talks more about ocean mixing there. Okay, anyway, I hope I didn't bore you too much with this video. Hopefully you do find it helpful. Again, you want to be an active reader. You want to make sure that you understand the key discovery, or what the essential question is on these science passages. You want to make sure you understand how the scientists kind of come to the conclusions that they come to and what they are and why they're important. And then as you answer the questions, you want to make sure that you can back up 100% of the answer choice with contextual support. Anyway, hopefully this helps. Good luck, and come back if you need help on any other videos or any other worksheets. All right, bye.